Okay, so I got one more question also from the homeworks, really excellent. So I wanted to discuss it. So here was the question. So at the Wilson-Fisher fixed point, what did we say? We said, well, the coupling was equal to 16 pi squared over 3 multiplied by epsilon plus order epsilon squared. And the question was, we didn't do an expansion in epsilon, so where do the order epsilon squared corrections come from, and how would you calculate them? Okay, so let's just discuss this now. Let me give you some ideas on how to think about this. Okay, so what went into this calculation? Let's just recap the logic. Well, we had the beta function. The beta function was 3 over 16 pi squared g squared. And so that was the beta function. Then that was the first input. The second input was that we work in 4 minus epsilon dimensions. And if you remember, one of the consequences of working in 4 minus epsilon dimensions is that now the coupling was no longer dimensionless. It was given by L to the minus epsilon. So we could define a dimensionless coupling, and the dimensionless coupling G bar was just given by G times by mu to the epsilon. So let's put a G bar here. So it's G bar that is dimension full, but G is dimensionless. And then the beta function that we studied was this one. Beta was equal to minus mu d by d mu of G bar. Let's write in G bar. There's a G mu to the epsilon. And we had two terms here. The one term was when the mu d by d mu hit the mu to the epsilon, and that landed us giving us a minus epsilon times by g mu to the epsilon. And then there was a second term, and that second term came when the mu d by d mu acted on g, and for that we used the value of the beta function. So we had 3 over 16 pi squared g squared mu to the epsilon. And then we said that when we sum these two terms, the beta function must vanish for a CFT. Okay? For CFT. Good. So let me put a little space there. Okay, very good. So this was the logic. Solving this equation, we get the value for G star, I should say G star. This is the value of the coupling at the fixed point. So notice a few things. So we start off and we imagine the theory has a coupling constant, and we've introduced a new parameter by saying we work in 4 minus epsilon dimensions. So it looks like we've got two parameters. Actually, we don't. They're related by the requirement that the beta function is equal to 0. So I really only have one parameter. It's the coupling constant and how far away I am from 4 dimensions. And those two parameters are coupled by the requirement that the beta function is 0. Now, this first piece over here, this first contribution to beta, this is classical. It comes from a classical scaling. So we've just looked at how things scale in 4 minus epsilon dimensions. Remember, this came just from dimensional analysis. So I'll put your dim analysis. And the final thing that I want to mention is that this is exact. Okay, so there's no approximation there. On the other hand, when we look at the beta function, this comes from interactions. So it's not from dimensional analysis. So it's from interactions. It's very much a quantum effect. It came from something a loop in a Feynman diagram, and it is only one loop, not, i.e., not exact. Not exact at all. So if you kept calculating, you would get all kinds of corrections to the beta function. So, for example, you might have a g to the 4 and a g to the 6, and so it would continue. So this is where we made our approximation. In our approximation, we just neglected these terms. Okay? So this is where we approximated. We just dropped those. Of course, if we're very close to 4 dimensions, so that epsilon is small, then the critical coupling is very small, and we can neglect the g to the 4 and the g to the 6 terms. So that's implicitly what we've done. But if we keep all of those extra terms, then down here, let's maybe add them in green, then down here, we would have had plus an extra g to the 4 plus an extra g to the 6, and so it would continue. So if we now set this to 0, well, you can see that g star's order epsilon. So if g star's order epsilon, the g squared will be epsilon squared, but the g to the 4 would be epsilon to the 4. The g to the 6 would be epsilon to the 6. And to cancel off these higher powers, we're going to need to cancel them off from this epsilon times g term. So to cancel these higher powers, we need now to take g star is some epsilon term. And in fact, here to cancel off the g to the 4, for example, I would need to add something with an epsilon cubed, so that then the epsilon times by the g would give me an epsilon to the 4. And so it would continue. Okay? You'd get an epsilon to the 5 and so on. So not too important what these powers are, but we would get an infinite power series expansion. And where would all of those extra terms come from? What is the function that we are expanding? It's beta. We're doing the expansion in g, but remember that g and epsilon are related by the requirement that the beta function is equal to 0. So a series in g is the same as a series in epsilon, and the beta function is a series in g. Okay, that completes the first chapter. Now we'll be moving on to the second chapter.